Βλέπω ότι είμαστε ήδη στους 70 παρακολουθώντας τη ροή στους participants.
Οπότε να μπούμε. Ξεκινήσουμε, Γιάννη.
Τα 5 ακαδημαϊκά λεπτά, άστα να περάσουν.
Ξεκινάμε, άμα θέλετε.
Καλησπέρα σας, κυρίες και κύριοι. Έχουμε σήμερα την χαρά να παρουσιάσουμε αυτό το webinar με αντικείμενο την ρομποτική της τεχνητής νοημοσύνης, με εξαιρετικούς συναδέλφους από το εξωτερικό. Και βεβαίως, όπως συνηθίζεται στα ανάλογα ακαδημαϊκά γεγονότα και συμβάντα και τέτοιες εκδηλώσεις, θα είναι η γλώσσα στα αγγλικά. Good evening, ladies and gentlemen. My name is Kyriakopoulos, and I am a professor at the National Technical University of Athens. And here today we have the honor to host a number of excellent speakers for the event, for the webinar entitled Robotics in the AI Era, Opportunities for Innovation in Greece. The Rector of the National Technical University, Professor Boudouvis, will make a few opening remarks. Andreas.
Καλημέρα σας, καλησπέρα σας. Good morning and good afternoon. I understand that we have attendees who are not Greek speakers, so I will speak in English. Dear colleagues, dear students and attendees, I am not a robotics expert, but I joined the co-organizing team of the experts, Kavraki, Kyriakopoulos and George Pappas, so as to stress the importance of the particular webinar for the community of the National Technical University of Athens, more generally for the engineering community, and especially the undergraduate and graduate students and young researchers. It is, of course, in a rector's job description to care about promoting state-of-the-art developments and steer the interest of those who can get actively engaged in new and promising endeavors. So it is that I kind of took the initiative for setting up this webinar along with my colleagues, and this came along with my participation in the board of HIAS, the Hellenic Institute of Advanced Studies. And let me say a few words about HIAS, under the auspices of which this webinar is launched, as well as other similar activities that will hopefully follow. HIAS started from a small group of distinguished academics of the Hellenic scientific diaspora with the aim to create bridges and serve as a hub for scientific exchanges between the diaspora and their peers in Greece. Also, to foster the development of international transdisciplinary collaborations on problems of societal relevance, including energy, health, artificial intelligence, education, environment, transport, maritime, agri-food, inequality. HIAS is founded on scientific excellence. It is inclusive and represents the strengths of the entire Hellenic scientific community. Among the primary goals of HIAS is to promote the involvement of the young researchers in activities of bilateral interest, with the involvement of senior scientists and their groups from both sides. The very first organized attempt of HIAS was to provide a setup of group of experts to work in order to deliver a vision for robotics in Greece. So a report came out entitled Robotics in the Artificial Intelligence Era, which is a white paper that hopefully will trigger a dialogue towards the development of a national robotics strategy. It is in the same scope that this webinar was organized. I thank very much our speakers, and I'm looking forward to an inspiring webinar.
Thank you, Andreas. And now we are going to turn the camera to Professor Lydia Kavraki, a professor at Rice University. She's the Noah Harding Professor of Computer Science, Bioengineering, Electrical and Computer Engineering, and Mechanical Engineering. And she's the director of the Ken Kennedy Institute at Rice University. Lydia received her bachelor's diploma in computer science from the University in Crete, and her PhD, again in computer science from Stanford. Her research interests span robotics, AI, and biomedicine. In robotics and AI, she's interested in enabling robots to work with people and in support of people. Lydia is a member of the National Academy of Medicine, the Academy of Medicine, Engineering, and Science of Texas, the International Academy of Medical and Biological Engineering, the Academia Europaea, and of course, the Academy of Athens. Lydia.
Kostas, thank you very much for this introduction. I'm very happy to be here, and I will get us started with a short introduction that will provide some context for this webinar. I will be sharing my screen. Does everything look okay?
Everything is all right.
Thank you very much. Robotics. Robotics is a young field. It is about 60 years old. In 1961, the first industrial robot, the Unimate, a material handling robot, was introduced at the General Motors. However, the concept of automata is a very old one, about 3,000 years old. In the Iliad, Hephaestus, the god of metalworking and fire, created automatic tripod carts to deliver nectar and ambrosia to the gods and goddesses on demand. Talos is also attributed to Hephaestus. A mechanical colossus made of bronze was imagined in the Argonautica. Talos patrolled the shores of the island of Crete, throwing boulders at invaders. In his treatise Automaton Making, the mathematician engineer Hieron of Alexandria, Hieron or Alexandres, describes a fully automated puppet theater that through a combination of displaced grain, axles, levels, pulleys, and wheels could enact an entire tragedy. Fast forward to the Renaissance, Leonardo da Vinci drew up plans for a robotic knight operated internally by weights and pulleys. In the 20th century, when industrialization became a reality, the word robot was coined in the 1920 play RUR, Rozum's Universal Robots, by Czech writer Karel Čapek. Chli was the first mobile robot with the ability to perceive and reason about its surroundings. The subject of SRI's Artificial Intelligence Center research from 1966 to 1972, Chli could perform tasks that required planning, route finding, and the rearrangement of simple objects. The robot greatly influenced modern robotics and AI techniques, and now it resides in the Computer History Museum. Today, robotics is one of the most disruptive technologies. Robots have already made great inroads in the automotive, semiconductor, manufacturing, and fulfillment sectors. Robotics is now poised to transform virtually every societal sector, including national security, agri-food, maritime, environment protection, infrastructure inspection, emergency response, logistics, transportation, healthcare, entertainment, and the arts. So the transformative power of this technology has prompted several reports and roadmaps in many countries, and I will encourage those of you who are interested in the topic to have a look at them. From Internet to Robotics, a roadmap for US Robotics 2020 editions followed earlier roadmaps in 2013 and 2016 in the United States and was a collaborative effort of several roboticists from academia and industry. The Robotics in the AI Era, a vision for a Hellenic robotics initiative executed under the auspices of HIAS, the Hellenic Institute of Advanced Studies, which co-sponsors this webinar, speaks more to the Greek idiosyncrasies and reality. From the HIAS report, I quote, "The global robotics market was valued at $62 billion in 2019 and is projected to reach $189 billion in 2027, growing at a compound annual rate of 13.5%. The market grows to 15.7 trillion by 2030 if artificial intelligence is considered. Today, when we use the word robot, we refer to a physical machine that can autonomously move within a physical environment, so embodiment is important, and can change the state of that environment. Defining robot characteristics are mobility, interactivity, communication, and autonomy. Hence, robotics is an interdisciplinary field that brings together hardware and software, increasingly guided by AI and machine learning. Robots can roughly be divided into two main categories: industrial robots and service robots. Industrial robots are used primarily in the automotive, semiconductor, and manufacturing industry. Service robots can further be divided into personal service and professional service robots. Personal service robots include home robots and entertaining robots, while professional service robots include medical robots, robots for agriculture, self-driving vehicles, unmanned aerial vehicles, and others. It is true that one can find examples where specific robots can execute with precision specific, very impressive tasks. Look at the coordinate somersaults of Boston Dynamics robots here in this video. And the solving of Rubik's Cube with a single magnificent hand by OpenAI. But the truth is that ways to customize, command, and deploy robot in service sectors remain elusive. Again, from the HIAS report, contrary to industrial robotics, which is rather mature, the service robotics sector, unmanned aerial vehicles, healthcare, logistics, and agri-food robotics is in its infancy and fast rising. Professional service robots is a 27 billion market worldwide and is growing at an annual rate of 30%. Furthermore, 20% of all service robot companies are young startups. This creates an exciting opportunity for aspiring Greek innovators to enter this young and fast-growing field and modernize the economy towards Industry 4.0. In this very short webinar, we have asked outstanding Greek scientists of the diaspora who work in robotics to give us a glimpse of their work and the things to come. We have also asked the Greek technologists and leaders in the industrial sector to discuss their efforts in Greece. We focused on advancements in aerial robots with talks by Alexis and Dimitris Stefanakis, autonomous vehicles with Margarita Chli and Katerina Fragkiadaki, social and rehabilitation robotics with Panos Artemiades, robots used in agriculture with Stavros Vougioukas, industrial robotics with Evangelos Theodorou, and underwater vehicles with Michael Triantafyllou. There is a lot we do not cover. There is no way that in a 2-hour webinar we can cover the current explosion in the material and engineering sciences that fuel robotics, the advances in robotic software that make robots more intelligent using AI, more connected using 5G, and safer for humans using the principles of collaborative robotics. Professor George Pappas will offer some concluding remarks. Before allowing all of us to enjoy the extraordinary talks that you're about to hear, I will leave you with some parting thoughts. Robots have captured the imagination of generations with what they could possibly do and how people would react to such advancements. And I'm not talking about ancient times here. Think about the film 2001, A Space Odyssey, the 2015 film Ex Machina, and think also about R2-D2 and C-3PO in the Star Wars, or the android child David in Steven Spielberg's film AI, Artificial Intelligence. The potential for good and the potential for harm are intertwined with any new technology, including robotics. Today, there is a real push to establish robot safety standards, robot technology standards, discuss privacy and cybersecurity in the context of robotics, and develop robot ethics. A country such as Greece and an audience such as you, with an excellent education and a culture of humanism, have the potential to develop niche areas in robotics and lead in putting technology in service to humanity. Thank you for your attention and enjoy the talks.
Okay.
Kostas, I think we can proceed.
Sure. And now we are speaking, we are going to attend the presentation of our first regular speaker, Alexis, Kostas Alexis, a full professor at the Department of Engineering and Cybernetics of the Norwegian University of Science and Technology, and the head of the Autonomous Robots Lab. And before that, Kostas was an associate professor at the Department of Computer Science and Engineering of University of Nevada, Reno. Prior to that, Kostas was working as a senior researcher at the Autonomous Systems Lab of ETH in Zurich. He obtained his PhD on unmanned systems control and collaboration under the supervision of Antonis at the University of Patras in Greece. He has been the principal and co-principal investigator within multiple national and international research projects in the US and Europe. And recently, his team, Kerberos, that he led, won the DARPA Subterranean Challenge and the $2 million prize reward. And most of all, I understand that a couple of days ago, he received an award or something like that. Kostas is going to tell us from the Senator of Nevada. Kostas.
Thank you. Thank you, Kostas, for the introduction. I hope you can see my screen, and I'm very honored to be here today in this exciting webinar organized by HIAS. So let me start directly in the interest of time and introduce what I will discuss. I'm going to discuss about aerial robotics, and I'm going to make the claim that the key aspect, and I think Lydia before outlined this also, the key aspect for robotics service robots of that type to be ubiquitous relates to a set of challenges, and the part of the work that I'm going to focus today is how we enable autonomy and a resilient autonomy in these conditions. Flying robots are now employing diverse configurations from classical multi-rotor systems, as we are all familiar now, what we call typically a drone, fixed-wing systems with long endurance, custom design specific for industry, and so on and so forth. But they are tasked to operate in very diverse and challenging conditions with perceptual degradation and other limitations that hinder the ability to operate autonomously. If I was to make a plot of what aerial robots autonomy relies upon, I will say it has to have three features: robustness in terms of having the same performance across conditions, redundancy in terms of actuation, sensing, and being able effectively to have the ways to operate against every error and in every condition, and resourcefulness in the ability to find a solution despite the challenges faced in all the other loops and functional subsystems. I want to relate today's talk with this challenge that Kostas mentioned, the DARPA Subterranean Challenge, which was also the reason that myself and my team received a recognition from the US Senate. The DARPA Subterranean Challenge was about robotic systems that are able to go and explore and map and search and characterize diverse underground environments. Underground environments are very tricky in the sense that they are not only large scale and confined. The largest mine in the world is 12,000 kilometers underground. It's massive. But they are also with low texture, visual obscurance. They can be dark, they can have smoke, they can have dust, and so on and so forth. There is no access to communications. So we're really talking about autonomous systems. I'm going to present the main part of the work that relates to our contributions, but the whole context is made through a large team and international collaboration that involves many partners. And the name is inspired by ancient Greek mythology, so it's called Cerberus, by the protector of the underworld. I got to know through this endeavor that actually underground domains are particularly important for the world and the society, and also very diverse. So we have tunnels and tunnel-like environments such as mines that gives us the resources, urban underground infrastructure that allows us to transport, and of course, the magical world of cave networks. DARPA, the US Defense Advanced Research Projects Agency, implemented a challenge analogous to the previous, like a DRC and the Urban Challenge, where robots had to explore and map and find objects in this type of diverse environments. In the final event, teams were tasked to explore parts that look like an underground mine, parts that look like an underground urban environment, and parts that were part of a natural cave. And we deployed a system of systems involving flying and legged robots. Legged robots were based on our collaboration with the team from ETH Zurich. To approach the problem, we performed, and we think it's necessary, and this is what I want to coin here, is that you need to perform holistic research across the domains of dexterous design of robotic systems and agile flying robots, resilient perception, resilient autonomy, alongside the remaining task-specific work such as detecting objects or enabling, of course, communications throughout. That's a picture of the systems we deployed in this competition. And again, I focus here on the flying part, although the legged robots played a particularly important role at the final event of the competition. Flying systems, speaking in terms of what are the core challenges, I think there are three. The embodiment has to be resilient, perception has to be resilient, and autonomy has to be resilient. A key aspect in our experience that allows for resilient embodiments is to make a design that is forgiving to last resort errors that can always happen. For example, that in a very confined environment, we can always collide a little bit with the world. So collision tolerance and other compliant designs are the means to facilitate such resilience. And if such a framework is designed, such a design is available, then we can build upon the more important functional autonomy loops that allow it to operate on its own, search, characterize, and explore unknown environments. These are some instances from previous robots of my team. People, of course, traditionally have worked with long time for control systems, flight control for these systems. And in my team, we employ a particular methodology called model predictive control. But very recently, we have, of course, ourselves and many other colleagues explore the potential of implementing and designing a control policy directly from data, allowing the system to directly also avoid the obstacles in the environment without having to undergo through the intermediate representation of building a map, which allows us to be particularly reactive and navigate with safety in an environment, even in the absence of complete localization information, which is what this little video on the right demonstrates to you. Beyond control and embodiment, I mentioned perception is a key challenge. GPS denied navigation is something that colleagues in the research community have explored heavily, either using LiDAR sensors or visual cameras and so on and so forth. My focus the last years on this topic related in particular to what we call perceptual degradation. And what we faced in the subterranean challenge, but also in other conditions, especially relevant to industry in the real world, is that robots do not operate in environments that are benign with simple features, good visual conditions, and so on and so forth, but they can be simultaneously GPS denied, dark, low texture, with smoke and fog and mist, geometrically self-similar, multiple kilometers in size, but at instances extremely narrow. To allow resilient localization and mapping based purely on onboard sensor data for flying robots, we have developed a multimodal localization mapping pipeline that first of all implements the sensors, which is a lot of effort in the hardware, as Lydia mentioned, to miniaturize everything for a small flying robot, to be able to see through degraded conditions. And here you see the benefits of thermal navigation, where the robot is unaffected by the presence of strong clouds of dust around it. But most importantly, to develop the methodologies that will allow to fuse diverse complementary sensors, such as LiDAR, vision, thermal cameras, and so on and so forth, alongside accelerometers and gyroscopes, to enable a unified complementary localization and mapping pipeline that allow us to know where the robot is, know the map of the environment at high accuracy and density, despite very dense clouds of dust, other obscurants, self-similar geometries, and so on and so forth. So if you think what it takes for a human to navigate a very complex cave or to perform search and rescue when there is an accident in an underground mine, then you understand the challenges these robots have to deal with and how difficult, but also how exciting it is to develop an avenue to embed resilience in such autonomous robotic systems. If this is given, or if there is a path for the research to enable resilience in perception and embodiment and control, then the next major question is to execute a mission that is useful for the end user, for us humans. And autonomy is the key task in that. We don't want to teleoperate robots. We are very happy with robots that are working together with humans, but we don't want humans to give low-level commands to robots. We want robots to be able to be treated as an intelligent agent able to undertake complex tasks. To that end, we work on a collection of path planning methodologies that allows us to co-optimize a diverse set of objectives in combination between what is important in the perceptual data, silent information, silent objects, and so on and so forth, and the action the robot should take. In our recent work, we developed a methodology that is uniformly applicable within flying and legged robots and allow to handle large kilometer-sized environments that have to be explored, for example, underground environments, in a manner that co-optimizes between what is the best viewpoint to maximize the new map to be explored, traversability constraints for legged robots because they have to deal with terrain, same as us having to deal with terrains as humans, ability to exploit the agile dynamics of flying robots, which can seamlessly navigate through the 3D space, and do so in a manner that works for a single system, but also works for a team of robots that have to undertake this exploration mission and mapping as a team, collaboratively. These are instances of these results where you see one of our flying robots exploring an underground mine in Nevada. And you see the thermal data and the visual, and the LiDAR data. And these pink paths are the paths that the robot has identified to navigate on its own in order to explore the remaining of the environment. And the robot eventually, by the end of the battery life, to make sure to come back to its origin and deliver the data to the people that wait for it outside the underground mine. This methodology in perception and in path planning was the core, the autonomy core of Team Cerberus, and in the final event of the DARPA Subterranean Challenge allowed us to win the competition, a result that I'm proud, not for myself mostly, but for my team as a whole, which managed to compete and win against teams from NASA and MIT, Carnegie Mellon, and others who had an inferior score in the last stage of the competition. And this was truly a big challenge for systems working or flying to be resilient and autonomous throughout. And it involved 3 challenges with different geometries at any time. In this map that allows to see the whole picture, you see 4 robots with 4 names, Cerberus, Chimera, Camel, and Cayman, taking paths in this complex underground topology and exploring these worlds. And eventually they deliver the map, but also the location of objects of interest in this map. And just for what it's worth, getting a point in the competition related to detecting an object correctly, reporting back the location with an error of up to 5 meters. So it was a task about navigation in austere conditions, mapping and detecting objects of interest. And the combination of walking and flying reflected the fact that ground systems, of course, have endurance, walking systems have dexterity against some terrain, but at the end of the day, when you have to go vertically up, get the bird's eye view, you also need the flying systems together. So that was a team that involved multiple robots, and this is the whole combination of robotic systems that Team Cerberus deployed through the 3 years of the competition. I want to close my talk highlighting that remote observation and mapping or search for objects is one thing that flying robots can do. It's really not the only one. And what you see in these videos is that we can, of course, exploit physical interaction to navigate through very confined environments. We are recently running a project that allows us to go through very narrow manhole settings where a human actually is able to navigate by just squeezing his shoulders, or to manipulate physical objects in the environment with a flying system. This is maybe not the most conventional application, but actually, if you think about it, it's very natural to the natural world, with birds, of course, being able to manipulate and interact with their environment. And of course, beyond small flying systems, I have to give credit to the period of the research that I was at TTH, together with my team back then, when with traditional fixed wing designs, glider, we demonstrated the ability of a system to fly during the day, charge its batteries with solar panels, and sustainably cross the night, and then fly the next day, and fly the next day. And eventually we call this the idea of perpetual flight. So this robot that you see here, 5.6 meters in wingspan, 6.5 kilos in weight, demonstrated in 2015, 81.5 hours of continuous flight, which is still the world record for anything below the 50 kilo class for an aircraft. With that, I want to highlight that an important aspect is to try to push the community as a whole. So we try to open source a lot of our work, and many of our colleagues today, I think from the talks, also work in this direction. I want to credit those that supported our work, but most importantly, I want to credit my team and everyone who is behind the results that you just saw. With that, thank you, Efcharisto, and happy to take any question.
Okay, I can see that we don't have any questions, so we may proceed to this next talk, which is going to be by a representative of the Greek industry, a very difficult industry, which is the high-tech industry in Greece, Dimitris Stefanakis, who has a master's in geographical information systems by the University of Aegean, and he has a specialization in remotely piloted aircraft systems. He got a PhD at the University of Aegean in 2019, and he has an experience of more than 4,000 hours of flight control of unmanned aerial systems and 50 years of experience for relevant R&D projects. And since 2006, he is into the unmanned aerial systems development. In 2013, he became a co-founder of Yukan Drone, where he's a company specializing, the first company in Greece that operates in the field of unmanned aerial system, where he's now the CEO of this company. and he's providing services and applications for aerial monitoring, surveys, mapping, and data analysis. Dimitri.
Hello, everyone. I hope you have my screen, and I hope that you're hearing me loud and clear. No?
Yes, we can hear you.
Super. Okay. I would like to thank the Professor for his kind words, and of course the Institute for organizing and inviting us here today for this webinar and this fine event. Of course, as Mr. Professor says, we are a vertical production line company, building and manufacturing, programming and designing advanced systems, and of course service providing, meaning that usually we have calls from professors like Mr. Kyriakopoulos asking for whatever payload or a pH measuring device or a thermal camera or whatever sensor robot, and the only valid answer that we can offer is, okay, Professor, what color do you like? This kind of work gives us opportunity to fly almost all over the world and be part of this unmanned system hype, if you like. The committee challenged us to investigate and present the uprising challenges of and of course opportunities coming along the digital transformation and AI in robotics. And the first thing that came into my mind is, oh my gosh, I'm heavily jealous and fond of all the students that we are speaking for today. They have the chance to see their work come to life and take action in everyday usage. And I think for sure there is no time like present. That's why I called this presentation the Wondering Solutions for a reason. In my area of expertise in the last 3 or 4 years, we are searching problems or clients, if you like, to propose our drones as Panakia. And that's why I didn't want to wear the tinkerer's hat today, but I really liked to give a business development aspect of all this of these opportunities. So silly guys like me love to explain stuff in a history manner. Thus, I only have 8 minutes or so to explain the evolution of robotics from a business aspect and how all these thoughts come together, and I hope you might find useful. So, in this phenomenon, it showcases the profound error we do. We use our area of expertise to narrow down our perspective. We're here, our ancestors, they're using outposts, acropolis, or high ground structures that simply changed their vantage point for a better overall view. After all these years, remote sensing and mapping and drones are doing exactly the same thing. Just reveal more information for the same narrow human field of view. So we had some prehistoric times. Except the lady on the right, if you don't know it, it's Marilyn Monroe handling a propeller from a target drone. The first attempts in the 19th century was, again, the defense industry could play with cool toys doing bad stuff. But after that, we have some medieval times where after the war ends, the remote control hobby came mainstream. And actually, if you think about it, today's drone scene is largely a continuation of this tradition, but with better electronics, of course. Like every history, we have the Renaissance. In the 90s, GPS came mainstream. We have the mobile phone hype, and of course, the internet maybe facilitates the open source movement, or at least I can send a colleague of mine a message and they can answer. But we're not there yet. Why? Because we have the age of alignment, of course, and of course, we can hands-on some real energy. We have, because of the battle of mobile phones, we have inertial and other sensors and GPSs that are small enough to use and cheap enough to use. And for the first time, last but not least, we have processors that we don't use for heating ourselves, but they can actually process. So around 2005 or 2009, somewhere in the middle, we start having all this hype about drones and all this open source initiative for flying drones for USVs or UXVs in general that we can play and use or make a hobby out of them. And of course, the academia embraced them and starting to use them a lot. So as I said in the beginning, there is no time like present. Nowadays, we can get hands-on in whatever device you can imagine. You can have sensors of any kind, and you can just imagine a solution and make it the other day. But after all this perfect storm, after this, there is no time like no present, we sat down and we starting narrow down to the tool, not the solution. Let me, we heard about the coding, the AI and buzzwords like machine learning, etc. So we narrowed down to the codex or something, or we said, of course, we need more miniaturized electronics and better sensors, etc. So we started to narrow down to this aspect. Or guys like me said that, okay, all of you can't do anything if you don't have a beautiful, shiny platform like mine. And everybody look his discipline without looking the solution. And once we found this panacea, we now hand down everyone who's willing to pay for them. So this gets me to my favorite slide. If you think about it, everybody from a scholar to a business guy just wanted to connect the physical with the digital world. And today's talk is all about the bridge between them, back and forth. So of course, yes, we have unmanned systems, or we have sensors, or we have measuring devices, or we have wearables. That's another hype. And as we talked about the processors, we have the power before leaving the physical world to start manipulating the data. Furthermore, one of the coolest things was communication, whatever communication, and of course synchronization. But there, you guys, you scholars and students that hearing us today, they are doing the magic. The magic is the word I use for things that I don't understand at all. But so using machine learning or AI, if you prefer, another tools and analytics. What are we trying to do? We're trying to disseminate our work. And how we can disseminate our work with different tools, with different interfaces, we can reach out more and more disciplines in a field of interest. But why? Because we need control to control the operational technology of the field without leaving one single day from the office. And that reminds me the IoT paradigm, or the AI paradigm, if you like, where we have things, whatever things, we have connectivity, we have data, and we have analytics. And this gives us the opportunity to leave the machine learning to handle this big data, since the world tends to be unmanned, using big data and AI, if we prefer. In short, we forgot the bottom-up approach, widely used in the Renaissance era, we said before, by not starting or evolving our technologies in regards to the client's desired pixel. If we stop focusing on a single expertise and combining AI and the huge amount of data we have in our disposal, we can either identify a human error bias in a traditional way of conducting something, but even better, come up with a new product or a new solution. I suppose you know the story about Leyland Stanford and the horses and the cinema, but that's another story for another webinar. Ultimately, combining the last slides, I found myself lucky and proud to work among this multidisciplinarity on steroids that robotics are come from. And instead of focusing in my polished and beautiful wireframes, I can stare at a valid solution with valid business ground and prospects. Here's a paradigm from the usage of an unmanned system. Instead of just mapping an area for fire fighting or for protecting the forests, it can be used as a relay or of communication. It can do edge computing and facilitate the biomass estimations, etc., etc. It can do a lot of stuff, but if it can be used from different disciplines. So, in concluding, of course, there are opportunities in the AI era for robotics, but like every opportunity, it has some challenges or a catch, if you like. And it's our burden to resolve the following issues. And we see that these humongous growth ratios that Ms. Lydia mentioned, 30 or 35 or 40%, annihilate culture, because we might have this the same thing that I'm envy for, that they have the same day our colleagues and students use the technology. You can see in the field, they don't have the time to get the appropriate culture, or a corporate culture, or a business culture, or an academic culture, etc. Also, it requires constant education and training in regards to see and identify your colleagues' job, even if he's not in the same discipline with us. Also, it heavily alters the wage status quo. We know the difference between the salary and wage, taxes, etc., but also we need to constant educating, so this goes to the wage status cost. Also, I heard about all these startups and spin-offs, but we have to challenge the classic paradigm of spin-offs or startups, where they hostilely acquired by big companies and deflate very fast. Also, one thing that I don't listen a lot, it's that the opportunities and the industrial digitization comes in a give and take manner. I have to commit, let's say as a businessman, I have to commit to my colleagues that I will pay for their constant training and education, but they have to commit to open their eyes and connect the dots or think out of the box in this era that we're living and taking. That was it. Thank you. And if you have any questions, I will be happy to answer them.
Okay. We see that we don't have a question for Dimitris. There is one question for the previous speaker, Kostas Alexis, but we'll take it at the end because we don't want to mix it. So we return back to the academic world, and we invite Maria Chli from ETH Zurich in the podium. Margarita is leading the Vision Robotics Lab, and she is Vice Director of the Institute of Robotics and Intelligent Systems, the famous IRIS lab in ETH Zurich. She's also an honorary fellow of the University of Edinburgh in the UK, where she held the Chancellor's Fellowship at the University of Edinburgh at the School of Informatics. She currently holds a Swiss National Science Foundation professorship. She obtained the bachelor and master's degrees in information and computing engineering from the University of Cambridge and the PhD from Imperial College in London. Her research interests are in computer vision for robotics, focusing on real-time perception for autonomous systems. Margarita.
Great. Thank you very much for this introduction and the invitation. I hope you can see me and hear me well. I trust this is the case. Good. So I'm going to talk about autonomous vehicles and systems with vision. And the pun here is intended to mean both oracy and orama, so both machine vision and vision for the future with respect to this topic. Now, when you hear autonomous vehicles and systems, I bet most of you think about autonomous cars. But I would like to open up your horizons to think a little bit broader about what kind of vehicles and systems we are working with. So there's so many other platforms, robotic platforms that one can think of. And at the Vision for Robotics Lab, we are aiming to basically use the onboard sensors and the onboard computation in order to automate their navigation in space. So we want to develop this robotic perception and intelligence for platforms such as the ones that you see here, in order to enable their safe navigation in space without colliding with their environment and actually performing a useful task. And the vision would be to take this a step further, even to have a portion of this team, or all of it, if you would like, to collaborate in a team to perform a common task together. Now, again, a team like this or a sub-team of such platforms, you can imagine that it can be very helpful for different tasks. Whether one wants to digitize an archaeological structure, to have a team to help in search and rescue, or to inspect the power plant or monitor crops, then robotic perception and systems can have a lot of impact and have a lot to offer. So back to our vision. So in order to achieve this vision, to have a team like this that is able to assist us in tasks as the ones that I shown before, then we have quite a few challenges to address. And for the purposes of this talk, I've partitioned these challenges into three main topics, basically. And these also represent the three main research streams in my lab. So I'm going to go through them and explain what I mean by these challenges and give you a taste of some of the works that we are doing to address them. Right, so what do we need for our autonomous vehicles and systems? First of all, we need them to be able to robustly estimate their ego motion in space, and also estimate what this space, what this scene looks like. Then we want them to build on top of that a level of intelligence up, if you'd like, to perform scene reconstruction such that they can interact with their scene, and also path planning in order to perform a mission like drive from A to B autonomously. And once we have robots able to address challenge 1 and 2, then we would like to exploit the fact that multiple robots might be deployed to perform a common task in order to do multi-agent collaboration, okay? Right, so let's look a little bit into what we mean with ego motion estimation. I'm glad most of you have knowledge of Greek, so you know what ego motion, can understand what ego motion means just by reading that. But the main idea is how to track the robot of emotion, or the motion of the robot while it is moving. And when you pause and think about this for a minute, you might say, you know what? I know what I'm going to do. I'm going to strap my phone on the robot that I want to track. I'm going to switch on my favorite Maps app, and I'm going to keep tracking where my phone, and hence my robot, is within this map, right? But of course, this has quite some assumptions underlying there. So for example, we assume that we have a good localization estimate and a good estimate of what that map looks like. And of course, you guessed it, we can not always rely on a good localization system, for example, indoors, and we cannot always rely on a good map because the world changes, buildings get demolished, new ones get built, right? So how do we do this? Well, we use onboard sensors, and I invite you to think about the sensors for the moment, or the rest of this talk if you'd like, to be a camera. So how can we track the motion of a robot that is equipped with a camera while it is moving? Now, when you're looking at this video on the bottom left, we humans are pretty good at understanding roughly how the camera has been moving in order to capture a video like this. The question is, how can we make our system understand how it is moving by looking, by basically performing estimates on a video like this? And the answer is that typically in the robotics community, in the robotic vision community, we pick natural scene features, these patches that you see here on the left, to serve as landmarks in the scene. And judging how these patches, how these landmarks move in image space from one image to the next, we start reasoning about the motion of the camera and hence the robot in 3D, as you see there on the right. And we call this task simultaneous localization and mapping. And for short, in the community, we refer to this problem as the problem of SLAM. And that's exactly our first challenge. How can we robustly perform SLAM for our robots, okay? So here is an example, and now it's, my God, it's 10 years old, this work. It's the first time that we were able to show that we can automate the flight of a small aircraft like this using a downward-looking camera and an inertial sensor. So here you can see the view, that map that the robot is building is very different from your typical maps that you use in your favorite apps, but it's enough to localize where the robot is and how it is moving in space. Now, in order to capture a video like this, there has been a lot of tuning happening, which brings me, of course, to the point that while we can see a very nice video like this, autonomy is still a big challenge. And for this reason, we resort to different research directions. One direction is to experiment with different sensors. For example, event cameras. Event cameras are inspired by human vision, by biological vision, if you'd like, and they capture changes in the intensities of an image, right? And what is great about them is that they can give us an insight into what happens in between traditional camera frames. They don't give us frames, they give us events, right? Just to tell us where these little pixels are changing in the image. So if I was moving in my video here, you would be able to see just the boundaries of my figure. So these cameras, they're very challenging because they defy all discrete time notions that we've been using as assumptions in the robotics and vision communities, but they promise to enable high-speed tracking and also tracking in darker scenes. So here you can see examples where traditional vision algorithms would fail. However, with event cameras applying our algorithms on corner detection, you can see on the right, we can still stably track some corners, which is the basis of running SLAM, of estimating how we're moving in space. Right, but apart from experimenting with different sensors, we also have other concrete problems to work with. And here you're looking at a video that has been captured while my student is walking down a pedestrian street here in Zurich. You can see the SLAM estimates on the bottom. That's the trajectory in red and our map in orange and yellow. And she's walking down one side of the street and coming back up the other side of the street. So basically this is a straight street. And frankly, these two places here, the green ones, should coincide, should correspond to exactly the same place. So what has happened here is that drift has happened. And no matter how good a SLAM system you're using, if you're not using global information and you're using only your local sensors, then you're bound to drift. And in instances like this, we are running place recognition. So this is the task of a robot recognizing when it's visiting an older location, and a location that it has seen before. And we do this by building a vocabulary of visual words and searching for images in the trajectory of the robot so far in a similar way like we do image search in Google. Now, some problems. Different places can appear the same place can appear very different, and even more so when you consider different seasons and different illumination. Now, if that was not enough, there's also the viewpoint challenge. That is exceptionally the case when you're viewing a scene with a drone. And let me focus a little bit here on this just to show you what we are doing at one of our works. So we wanted to push the boundaries of what place recognition algorithms can do with respect to viewpoint tolerance. Here you can see the different viewpoints that we are aiming for. And here are some results on a planar scene just for simplicity, where we are actually capturing both the visual information, but also local geometries to help us recover place recognition instances such as these. So you can, focusing on the top, you can see the very different viewpoints that we're capturing the world by, which is a real challenge for visual perception. Now, with respect to illumination and seasons, the community in my lab, we are resorting to deep learning techniques. So here's beautiful examples of this algorithm that is using convolutional neural networks to tell us whether we are visiting a place that we have seen before. So this is trained in images from June and from February. So we have very different instances. So the system here learns the information to suppress and the information to use when asked, have I been to this place before? Right, so I bombarded you with information, and I'm sorry, I guess the whole talk is like this, but I want to show you the wealth of challenges that we're dealing with here. So for the first challenge for robust SLAM, we've been experimenting with different sensors, sensor fusion, deep learning, right? In order to form this backbone of the awareness of space for a robot to automate its navigation by giving it a sense of its pose, where it is in the world, and a sense of the map. So, but a key word here is that this map so far has been sparse, which brings me to the second challenge that we are dealing with, scene reconstruction, such that our robots are able to reach out and grasp an object or to avoid obstacles while flying. So imagine a robot that is intelligent enough to override the pilot's commands when he or she is driving it through a wall. So how can we do that? We need to build denser maps for this. And here you're seeing an example where using a single camera, we are able to achieve this dense gray colored 3D reconstruction that is superimposed against the red laser point cloud there that is used for ground truth. Now, you can see this is far from perfect, but one can argue that this is more than enough in order to enable local obstacle avoidance for our drones. And it is with maps like this that then we can run automation, path planning missions, like what you see here. So in this example, the drone is tasked to cover, 3D reconstruct the area that is looking at, and the squares that you see there in different colors, they're it's evaluations of poses in the surroundings of the drones that we believe they will be informative. And let me share with you a little bit of an insight into how this works, and I will leave Yves give you his.
We present a path planner for 3D reconstruction of large scenes for an MAV equipped with the gimbal-actuated camera. Potential next best views are sampled from the MAV's configuration space and ranked by their expected information gain. The information gain of a proposed viewpoint is calculated with the raycasting operation and encodes visibility of frontiers, visibility of unknown space, as well as quality improvements of the reconstructed surface. In this more intricate bridge scene, the actuated gimbal seems to be necessary to fully reconstruct the scene. Without the gimbal, the underside of the bridge is not fully observable, leading to gaps in the mesh. Our planners also perform well in large indoor scenes. Not only is our approach faster, but once again, some surfaces are only observable with the actuated gimbal.
So with works like this, we're able to push what we can do in terms of quality of reconstructions, but also speed of reconstructions. And within the same umbrella of trying to build in more intelligence to our robots, we also use semantics. We can also use semantics when driving a robot from A to B. For example, to avoid areas that can be difficult for a robot to estimate, to perform its estimates, where it is ego motion and scene estimation. And here you're going to see some examples, some experiments in different scenes. We are comparing our planner on the bottom right with different planners and in different scenes. And we can show that using semantics, for example, to be able to understand whether this part of the scene corresponds to water or whether this part of the scene corresponds to a busy road, then we can guide our robot to avoid navigating on top of such areas such that it's able to perform estimates more robustly. In the interest of time, I'm going to skip forward to go on to the third challenge on multi-agent collaboration to show you a taste of what we do here. So imagine having a team of drones that is taking off and knows nothing about the scene. They start running SLAM on board their own processors, right? As I explained before, they're building their maps, and And before forgetting their maps, because they have limited space on board, they're sending all this information down to a server or up to a cloud, if you'd like, that acts as a bookkeeping entity. And through this centralized architecture, the drones can collaborate with each other to join their forces to build common maps and share information about the environment. And when you think about multi-agent collaboration, where we're going with this, sky is the limit, right? So you can think about robots-to-robot collaboration, as we've seen with drones in this video, or human-to-robot collaboration to perform tasks together. And I argue that with these three challenges, we're aiming to push robotic perception and collaboration, because we believe that these are key to pushing robotic autonomy. And I use this example from nature to show you also how collaboration can help to do more than what one or two agents can do by themselves. Right, and I used most of the talk to show you videos with respect to drones, but the extension to other platforms is also feasible. And indeed, we have some examples with automating train navigation, with having phones to use to play games in the virtual world, and it's all using the same basic notions that we've seen in this talk. And I have one last video to show you with this autonomous excavator. I think it's pretty interesting to see. This is a joint effort by roboticists and physicists and architects. We joined forces to use basically an autonomous excavator equipped with lidars and cameras to build a wall out of locally sourced stones like these. So we are scanning the environment, and then we're using a physics simulator running in the background to figure out how to place these stones such that we're able to build a freestanding wall using this autonomous excavator. And within the course of several days, we were able to build a wall. You're going to see it in a minute. It doesn't look very nice, but I think it's interesting to see what robotics can do, what robotic autonomy can do. And imagine having had two robots able to build this, right? All the challenges and opportunities that would have to go on there. And with this, I would like to thank you for your attention and take any questions, if any. Thank you.
Yes, Margarita, you have two questions. Please look at your chat. Please, if possible, you read each one of them. And since in order to keep the timing proper, okay. Try to answer them in 2 minutes, if possible. Thank you.
Okay, so I do my best. So in case you think that this is going too long, I can type my answer. But I can at least try to address the questions. So I wanted to ask Dr. Chli if there are challenges in the information transmission bandwidth as the robot moves away in closed spaces, high interference from the control center, assuming this is separate. What can be done to mitigate any issues? Of course, communication is a big problem. This is something that I constantly try to talk with my colleagues because I'm not an expert. For the moment, we're using Wi-Fi routers to communicate, but of course, this is not secure and not robust enough. In some of our works, we try to use ultra-wideband information between the drones to basically estimate how far they are from each other. But let me assure you, this is a very on-point question and an open question, I would say. Second question and last one, is SLAM applicable for mini applications, such as creating a map of a desk that has different machines on top with sensors from a mini mobile robot platform in a way that the map can be stored and the robot can go in front of each machine when ordered? Okay, yes, of course, SLAM is applicable in problems like this, and you can consider your desktop as the workspace. You can consider your floor as your workspace. Now, SLAM is the very basic notion, the very basic capability that needs to be encoded, but then we are building, you need to build layers on top of that, such that you're able to assign labels, like, for example, this is my book on my desk and this is my laptop on my desk, such that then your robot knows that when I'm planning my path to the to the laptop from the book, then you have these notions or, to consult. But basically, SLAM is the underlying principle. And then on top of this, we are running reconstruction, semantics, path planning, etc. So with this, I would like to thank you and apologies for taking more time. Thanks.
Thank you, Margarita.
Costa, turn your microphone on.
Okay,
Please.
sorry. And then we are moving to the next speaker, who is the, I must say, the youngest member of this team, and therefore a very dynamic, Katerina Fragkiadaki, an assistant professor in the machine learning department at Carnegie Mellon. Before that, she was a postdoctoral researcher at Berkeley and later at Google Research in Mountain View. She completed a PhD in the famous GRASP lab of University of Pennsylvania, while she did her diploma studies at the National Technical University of Athens. She is interested in building machines that understand the stories that video portray, and inversely, in using videos to teach machines about the world. Katerina.
Yes, thank you very much. I'm very happy to be here. I'm very happy also to see my professors here on the attendee panelist list. I will discuss about home robotics. Apologies for my voice. It's a little bit, it's from an illness. So home robotics, very complementary to the previous talks. I will focus more on computer vision because this is my background and language understanding and what we need for human-robot collaboration. So here is Amazon Astro, a little robot that was released by Amazon earlier this year. It has amazing SLAM capabilities, and we learned a lot about SLAM from previous talk. It has this nice eyes, so a big part of this wonderful little robot is the design, the product design. I cannot say it does many different things. It can follow the human, it can go to the dining room and kitchen and so on. It cannot manipulate, it doesn't have any end effectors. But many companies, for example, Amazon, Sony, Toyota, are looking into that direction of home robots and many others. So the question is, what do we need more to get useful home assistants in our households beyond Alexa, beyond machines that can just sit and listen without looking around, without moving and so on. I just also want to point out that recently there was a simple challenge was announced. In fact, we are part of that simple challenge by Amazon, a competition among multiple teams of how to develop agents that can listen to human instructions and conduct a dialogue to clarify misunderstandings or to ask for help and complete the instructions in the environment, such as finding objects, cooking, opening, closing fridges and microwaves, and so on and so forth. And here's another concrete application from Sony, who has launched the project of gastronomy, Sony AI gastronomy. We are also part of that project. So here is a picture from an advertisement video of the company where they imagine this kitchen that has different arms that can listen to what the human is doing, can see how the human can cut, let's say, a lemon and so on, and continue further the process. And this concerns both the cutting and the plating of the food as well as serving of the food. So we're collaborating with Sony on that direction. We are 3 professors on perception, manipulation, and interaction. So all the way from, seeing the ingredients, trying to arrange them, cut them, put them on the plate and serve them to the end user. And of course, this is right now, it sounds like science fiction, but this is what we're working on. So I want to discuss about open problems today. And so this is going to also give us the opportunity to discuss the solution we're trying to pursue. So one clear problem is, how do we understand and how do we generalize beyond the training distribution? How can we have robots that have common sense, understand temporal and causal associations between concepts, and can transfer this common sense across multiple environments and tasks? This is absolutely necessary if the robot is to act without actually being instructed by the human. Or if you see a person fainted on the floor, you need to call 911. You are not supposed to be instructed. As well as we want to be robust to adversarial users or to users that are tired, users that have a lot of missing information when they give and so on. Common sense about the world is absolutely necessary for human and robots to understand one another. And interaction, interactive learning, how we learn on the task instead of just training the robot and then deploying it. So I'll give you a little bit of, sprinkle some, projects that are going on my lab on those directions. So one direction we have is how do we build these embodied assistants that I just said. So this is our first version of tidy, teachable, interactive, decluttering, embodied explorer that essentially is a little robot that goes around the room, around your house, detects objects, figures out if they're in and out of place. And if they're out of place, then it takes them and puts them to the right place. And you don't need to say anything. You can teach the robot of what you like the common sense placements to be in the beginning. But even if you don't say anything, the robot has its own launches from the previous training environments. And of course, this robot, this assistant has a very basic mapping and planning pipeline that needs to go around, build them up on the environment, detect the objects, keep track of its locomotion as it's moving around, define for every object where they're in and out of place. And this is where the common sense comes in the form of previous visual memories and symbolic memories. So this is the knowledge of the agent is a big graph. We call it the memics, where nodes are different objects it has seen before, and edges are their contextual relationships, who supports whom, who is next to whom, which objects show up in different rooms, and so on. And the agent, what it does is essentially moves around the room. And this is not a real robot. It's a robot in a simulated environment. Okay, and there are many, many simulators right now exactly to encourage research in that direction. It detects an object, it detects its label, it goes into its memory, and it tries to predict where it needs to go back and put it. And then it needs to actively search for that placement in the back and place it back, and then continues like this. For humans to be able to communicate with robots need to be able to understand language. And the way the verb understand is difficult, but we think we can summarize in three concepts. First, we should be able to detect what the human talks about. Second, we should be able to generate and imagine, even if this object is not visible, we should be able to imagine what the human is talking about. And third, we should be able to combine detection and generation to alter the scene so that we can understand the goal that the human is trying to convey. So if we look just in the first case, we have a system that instead of just opening its eyes in the scene and just detecting all the objects, it actually takes as input a language phrase that guides it to find the right object. So here, as you see, you take this scene is full of objects, full of entities. If you just run detectors, all of them are going to fire, despite the fact that the object that the human was talking about, there's no reason this bottom-up detector is going to find it. But with top-down modulation from language, this box can be detected, both in 2D scenes as well as 3D point clouds. And if all of the students that will pursue this direction of vision and language and so on, a lot of it is about designing the right network architectures and putting the right inductive biases in these architectures that we're looking for. Okay, so now essentially you go from an image and a description of a label of what the human is looking towards grounding, finding the boxes, the segmentations of what that object is. Now, a big philosophical question is what is perception? What's the goal of perception? Perception is not about labeling the visible pixels, but rather imagining the invisible, the 3D world that is behind the 2D picture. And if you want to play it, if you want to do a cooking robot, as what I discussed earlier, when I show you this image, all of us understand that it is not the object that stops exactly there, that this cracker continues behind the occlusion. So we want systems that take as input images and spit out segmentations and completions behind the RGB image. All right. So for this to happen, we need to combine feed-forward detectors with generative models. And indeed, this is the cortex. What we think is in the visual cortex, there are a lot of top-down pathways that essentially constantly render and try to imagine what it is in the picture, while currently our state-of-the-art detectors are feed-forward. They go from an image all the way to the label without trying to generate and imagine alternatives. So one thing we're looking into is exactly how do we combine detectors and generators and with fast and slow learning. That's what we call fast and slow learning. We want our model to be able to spend more time in an out of distribution scene than in a scene that it knows a lot about. Same as the human, that when you are in an environment that is not very familiar, you spend more time trying to understand, make sense of what you see, as opposed to a familiar scene like the kitchen in your house. So we have developed networks that we call fast and slow generative networks that essentially they perform a search of how to understand things that are completely out of distribution. That network here was only trained on individual primitive surfaces, rods. It has never seen those assembled into chairs and tried to make sense of a very new object. And again, I don't want to go into the details, but it is very important. How do you allow in your network architecture to bind information about different entities into different slots, into different registers, as opposed to just representing the scene as a mush of features, just feature maps. The same way when you see a scene, you see the window and the radiator, and then the nose and the eye and so on. You don't just see featurizations, all right? So the question is, how do you build this entity recognition, essentially a mechanism into perception, okay, the state-of-the-art perception systems. So again, in that the same vein of not labeling the visible, but imagining the invisible, we have developed networks that take 2D images and spit out 3D feature maps, essentially 3D grids where every location is a feature vector that describes the content of the scene at that location. We call them geometry-aware recurrent networks, okay? And you can learn those from videos simply by predicting viewpoints, much like a human. Once you are able to go from 2D images that constantly change based on how the viewpoint changes and the scale changes when you go close and far, once you have a stable 3D perception, then you can do better prediction of where the objects are going to go. Your prediction and your physics simulator and the world dynamics you're going to learn will not depend from the viewpoint. They're going to be invariant from the viewpoint, so you can do this inference from any viewpoint. And you can use the same 3D features to develop different manipulation techniques for different objects, as we do here. And it seems that I don't have the time to go into details. So open problems. So 2 slides on open problems. I think the real big problem is how do we endow robots with the common sense and the concept hierarchies and percept hierarchies that humans have. We do not want this image to be labeled as bus. When we see this image, we know there's something wrong. We know usually roads are supposed not to be blocked. There is this bus that actually, we know what happened before and we know what's going to happen after. How can we endow our machines with this type of contextual notions so that when perception happens, there is a homogeneous associative memory of previous events and memories and abstraction of those memories that will allow the robot to reason about the current picture, as opposed to just detecting the objects. And the last slide is as follows. This common sense is absolutely necessary for our robot to be able to have a dialogue that makes sense with a human. Here, you see Mena, which is a Google chatting assistant, very, very recent one, that says that he's learning Cantonese, while at the same time says that he's a native Cantonese speaker. So this is not possible. Even worse, the same agent here says that his favorite band is Avenged Sevenfold, and his worst band is also the same band. So he doesn't know that the most and worst cannot be the same things. So that's my last slide. I think learning should be embodied, self-supervised, interactive, and continual. And I'm happy to take any of your questions.
Okay, Katerina, I think that you have one question. It is in your Q&A. You may read it and answer it if you want.
Yes. So it says that since there is a vast amount of different item geometries, would there be a value in creating an open source database with common household items, maybe crowdsourced to assist any home robot using vision to complete common tasks? Yes. I think this question says, why don't we just try to not start from scratch? Just start from a huge database of how objects look like. This is absolutely true, and this database exists. There is, for example, the Sapiens dataset, which is a huge dataset about all possible doors that you'll ever be able to find in houses or a lot of indoor objects and so on. The question is, these databases, need to be in a form that they need to be used by perception. So it's not just enough to leave them there. You need to learn to go from renders of those databases to the output, which is, okay, the 3D point cloud. In the same way that self-driving car companies do not just give a big database of here is how cars look like, but rather they label cars in actual streams. Okay, so this is the pre-training we need to do. But yes, actually our generative fast and slow work also believes in this. We need to teach the primitives, but we need to teach the primitives from images, not just to give you idealized forms of those primitives in a database. Yeah, thank you for your question.
Thank you, Katerina. And then we are moving to the next speaker, Professor Panos Artemiades, that received the diploma in mechanical engineering in 2004 from NTUA. And then he proved that he is a survivor, as he managed to get a PhD under my supervision in 2009. Later on, he worked as a postdoctoral research associate in the mechanical engineering department at MIT, Massachusetts Institute of Technology. And then he worked as an assistant professor in the mechanical engineering department of Arizona State University. And now he's an associate professor in the same department, mechanical engineering department, but at the University of Delaware. His research is at the interface of human and robots. And he's trying to answer complex questions about the fundamentals of merging machine capabilities with the human brain, with the purpose to improve the quality of life and work by developing and controlling robotic devices that physically and cognitively interact and collaborate with humans. Panos is the recipient of the DARPA Young Faculty Award and the Air Force Young Investigator Award in 2014. Panagiotis.
Thank you, Costa. Thank you all for being here. Let me start with a fun fact. Exactly this day, 13 years ago, I actually defended my PhD in the mechanical engineering department. So it's really an honor to be among these companies today. So let me actually switch to robots that actually physically interact with humans. We have been talking about aerial robots and robots that are in our house, but what about robots that we wear? And what about robots that we physically interact with? So this is what I call healthcare robotics related to mobility. These are 3 examples of the robots and the research that I'm going to talk about today that we do in the lab. I'm going to start with assistive devices, then we go to rehabilitation devices, and then prostheses. As Lydia said in the beginning, the challenges of robotics have evolved. Back in the 60s and 70s, we were talking about speed and accuracy and repeatability of those robotic manipulators that were working enclosed in robotic cells away from humans. And now we go to much more significant challenges when we interact with humans and when we interact with the human body. So we're talking about safety in human interaction. We're talking about adaptability to different body shapes and different capabilities of humans. We're talking about robustness and, of course, comfort and safety for wearable systems. And, of course, energy efficiency. Nobody wants to be plugged on the wall when is wearing a robotic device or a prosthesis. So we're talking about batteries and energy efficiency of those robots. So definitely the challenges in robotics have evolved through time, especially as robots come closer to humans and are worn by humans. How important is this problem? How important is the problem of mobility and how robots can help with that? First of all, we all know that we are an aging population, right? And the percentage of people over 65 years old is actually increasing. It's increasing dramatically. On the left side of this slide, you see that in a few years from today, adults over 65 years old will be more than children under 18. And only by 2060, about a fourth of the population will be over 65 years old in the US. And on the right, we have the same more or less statistics from the United Nations. And as you see, the current population of people over 60 will double in 30 years from today. So we're talking about aging population. And of course, we're talking about mobility problems. And let's see how robots can help with that. It's not only aging, it has to do with stroke and any kind of cardiovascular disease. that mobility is affected. If this figure here on the left represents the world population over 25, unfortunately about 25% of them will have a stroke in their lifetime. And a third of them will unfortunately die due to complications of stroke. And the remaining 2/3 will need some kind of assistance and some kinds of rehabilitation. So the question is how robots can help with that. And to be honest here, stroke is not only a physical problem, it's actually financial, a very costly process throughout the world. On the left, you see some stats from the European Union. What I'd like you to see here is that only 1/3 of the cost has to do with the stroke and the healthcare itself, the cost of the healthcare itself. The remaining has to do with indirect costs that essentially emerges if the person has mobility issues or physical disabilities. The numbers in the US are even worse. As you see on the right here, we're talking about $46 billion in only 2014, 2015. So robotics can definitely help. Now that we have safer robots and we can work with controllers that adapt to humans, we can definitely help. This is just a statistic from the rehabilitation robotics market. This is only private sector. And as you see, it has really skyrocketed in the past years and will continue like that. It will probably double in the next 3 to 4 years in terms of market value. So let's go. So along those lines, this is the mission of my lab, the Human-Oriented Robotics and Controls Lab, which essentially can be summarized in improving the quality of life and work by developing, modeling, and controlling robots that physically or cognitively interact with humans. We have done a lot of work with prosthesis, lower limb prosthesis. I'm going to present briefly today, mainly rehabilitation robotics, how we can use robots to rehabilitate after a stroke. And we have been doing a lot of work on how humans can interact with multiple robots through brain interfaces. So starting with rehabilitation, the news are actually good for upper limb. This is something that started back in the late 80s from MIT Manus and the MIT group on how we can use robotic devices to rehabilitate upper limb motion. And this has been doing very well. Now there are multiple hospitals around the world that have robots that are actively used almost every day to rehabilitate patients for upper limb motion. And actually the latest American Heart Association report says that they actually recommend robots for upper limb rehabilitation. Lower limb is a completely different beast. Walking is much more challenging. Right? It has to do with balance, has to do with transfer of weight. And unfortunately, the reports are not good so far. The robots that have been used so far in rehabilitation for lower limb have not been as successful as for upper limb. I would like to make a claim here that so far, all the robots that have been developed for lower limb rehabilitation have been passively moving limbs. And we know from the neuroscience and the neuroplasticity of the brain that this is not going to work. Passively moving the limbs in order for a patient to walk is not going to lead in rewiring the brain. The brain has a very nice property that has to do with neuroplasticity. It's able to rewire and reconnect itself or different regions of itself, but this cannot be done with just passive motion. So you have to engage into more dynamic, into more forceful interaction with the robot in order to engage the brain and rewire it. So let me start with a goal or really a bold idea that we had about 8 years ago is how we can provide therapy for the paretic leg. Remember that stroke is usually hemiparetic, so one of the two sides is affected, the other is still intact. So the idea was how we can provide therapy to the paretic leg by using physical interaction with the healthy leg. So now we're not messing around with the paretic side, we're actually engaging with the healthy side. And this is based on the fact that those two legs need to collaborate in order for us to walk. The brain is involved into interleg coordination mechanisms. And is it possible to provide rehabilitation and rewire the brain by engaging this interleg coordination that is still active after a stroke? For that, we developed the variable stiffness treadmill that you see on the left. This is a unique split belt treadmill that for the first time, it can interactively change its vertical stiffness. So essentially you walk on that treadmill and you feel all kind of different stiffnesses or compliance of the ground that you want. This is controllable in real time and has a wide range of stiffness. But as a mechanical engineer, I would like to be able to model what's really going on, apply controllers to that so that I have the optimum outcome, which is rehabilitation and better functional outcomes of gait. So lately, the past 5 years, we have been working on models, on neuromuscular models that really explain how the brain, how muscles coordinate for humans to walk. We actually started with a model that was already available back in 2015 from the group in CMU. This is a really complicated model. It has at least 12 muscles for each leg. It includes neural pathways and both high level and low level. And then we added what we call the high level controller on that model. In order to model what really happens in this variable stiffness treadmill and what happens during the process of engaging one limb and having the other limb reacting to that. So you see here on the top left, you see a video of the actual treadmill and how you can unilaterally change the stiffness underneath the left leg. On the bottom, you see how our new high-level controller included in this neuromuscular model can actually result in a model behavior that very closely resembles the human. And this is the first time that we saw that a very complicated neuromuscular model that explains how the brain controls walking can be retrofitted to this idea of variable stiffness, and it can actually match what we see with real human subjects on the treadmill. So then we did the next step, the next obvious step, which is, okay, can we now that we know the model of this process, can we try to optimize it to provide rehabilitation? So we did an experiment where we have now repeated stiffness perturbations, and the holy grail in rehabilitation is the after effect. So you do this training session with your subject for 10, 15 minutes, 30 minutes. What's the after effect? They would just walk away in the lab and they just walk as bad as they came in. So we are focusing now on characterizing this after effect. And this is for the first time, the top right figure that you see on the slide. For the first time, we see an after effect that lasts for at least 200 gait cycles, 200 steps after we remove the perturbations. The best so far has been 10 to 15 gait cycles after you remove the perturbation. And now we see that by introducing this optimality of interventions and optimality of perturbations through this treadmill, you can see an after effect that lasts much, much longer. And our hope is to now transition to therapy for those stroke subjects so that they do this kind of session twice a week and they have a long-term effect with specific functional outcomes or better functional outcomes for gait. We're also interested in this idea of visual interaction and visual feedback. So we are also playing with virtual walls as they walk on the treadmill and want to see what can we improve in terms of functional outcomes again on gait by also having some visual feedback. So let me switch, since I only have a few minutes, let me switch to the second project, which has to do with prosthesis. So this is actually a collaboration with industry. NSF has these unique mechanisms here to fund projects in collaboration with industry. So now we have partnered with Spring Active from Tempe, Arizona, for the controller development of their prosthesis. So this is a prosthesis, a lower limb prosthesis that they developed. And what we are doing is improving its controller so that it is robust in dynamic environments. And what I mean by dynamic environments is along the lines of this variable stiffness treadmill device that we have in the lab. What happens when you walk on very soft environments? Not only hiking on uneven terrains, but also very soft environments. So you can imagine yourself, walking on sand in a nice beach in Greece, where you have a high compliant or a high dynamic, highly dynamic surface. What happens with the control, or what needs to be done with the control of this prosthesis in order to be robust and safe for the user when we transition between those dynamic environments. So a work that actually was submitted literally a few days ago how to do with how we take a well-established model. This is called the 3D dual slip model that is mainly used in bipeds, in locomotion robotics. How we transitioned that model, how we extended that model in compliant surfaces, and how then we design a controller that's essentially an optimized LQL controller that had to do with you do a pre-stiffening, you adjust the stiffness of the legs, and that proves to be robust and actually guaranteed stable in terms of walking on very soft surfaces. We actually tested the system in simulation, and we saw that the range of compliance that you can achieve is really big. You can go to a surface that is about 30 kilonewtons per meter in terms of stiffness. Just to give you an idea, a very soft mattress, like a gym mat, is in the order of 60 kilonewtons, so we can do much softer surfaces than that. So this is a work that we just completed in simulation. Now we're transitioning to implementing that idea of pre-stiffening your leg into the actual prosthesis that we have in the lab. Lately, we have been also working on how to introduce the human in the loop, how we can use signals that are coming from the muscles of the residual limb when you have an amputation to intelligently control the prosthesis, again, in terms of transitioning to different surfaces and different compliances. I will stop here by thinking about the future. What are really the challenges for healthcare robotics, and especially those robotics that have to do with mobility? One important thing is inherently safety. I don't want to wear a robot, or I don't want to have a prosthesis that will not be safe, even if it loses completely power. So we're thinking about safety, not only in terms of control, but also in terms of the hardware. That's why there's a lot of hype around soft robotics lately. I'm a big supporter of the idea of model-based therapy. I think we need to go beyond the empirical formulas for medicine and for providing assistance, and go and do some really model-based work in order to optimize our interventions. And in terms of prosthesis, we need to think about controlling those prostheses in a better way to be robust in dynamic environments for everyday life tasks. I would like to thank you all for the attention. I would like to take the opportunity to invite you in the University of Delaware. I don't want to obviously contribute to brain drain, but I would very well welcome students from Greece, and actually I have a couple here in my lab to spend some time here and essentially formulate this bridge that the Hellenic Institute for Advanced Studies wants to do. So thank you a lot for your attention.
Okay, thank you, Panagiotis. We proceed now to the next speaker, Professor Stavros Vougioukas, a graduate of the Aristotle University of Thessaloniki, with a master's degree in electrical and computer engineering from SUNY Buffalo, and a PhD in robotics and automation, the electrical and computer systems engineering department, my personal also alma mater at Rensselaer Polytechnic Institute in 1995. Then he worked as a postdoctoral researcher at the Parma, Italy. And then for quite a few years, in other words, until 2011, at the School of Agriculture of the Aristotle University of Thessaloniki. As a result of the amazing brain drain that we had during crisis, he moved to the University of California, Davis at 2012, and he joined the Biological and Agricultural Engineering Department, where he's a professor. He works in the area of agricultural robotics and automation for specialty crops. And he focuses on robotic and robot-aided harvesting and on the design, development, and testing of actuators, perception, and control systems for optimal management of inputs and products. Stavros. Stavros.
Thank you very much, Costa, for the introduction. I'm really happy to be here and be presenting my work. Just as a brief introduction, this is where I am now. This is the University of California, Davis. We're about an hour and a half to 2 hours from San Francisco and the Silicon Valley, and about 3 hours away from California Central Valley, one of the most productive areas in the world. I run the Bioautomation Lab. We are very active in collaborative robotic harvest aids. mechanical and robotic food harvesting, and autonomy and mechanization for orchards. So if you go and Google agricultural robot, which is what I did yesterday, and print out some of the images, you will see a lot of different robots out there that are intended to do harvesting, weeding, spraying or pruning, seeding, thinning fruits and flowers, fertilizing, transporting, anything you can imagine. You will find a robot that is aspiring to do that in commercial agriculture. Now, what is driving the need for all those robots? Well, these robots are offering precision sensing and actuation services. And there are two main application areas for them. One is precision farming. Precision farming is about applying the right type and amount of input, for example, chemical, at the right time, at the right place. The goal is to maximize production, minimize the inputs, and do it in a sustainable fashion so that we reduce the footprint of the technology on the environment. So this is one of the major drivers. The other major driver is the reduction of manual labor. This is a huge problem in most parts of the world. We actually need to either replace farm workers or work with them and increase their efficiency. Now, in terms of precision farming, and because I understand that some people in the audience may be interested in startups or in translating the research into industry, precision farming has two different domains. One is the large row crops, soy, corn, wheat, etc. This area is dominated by large equipment manufacturers, and automation is mostly embedded in their machines. And all of those machines are GPS guided because it's pretty simple to navigate in open space pretty much without any obstacles. On the other hand, when we deal with specialty crops, fruits, vegetables, vineyards, orchards, this space is dominated by startups, mainly because the market is very fragmented, but the challenges there are different. And I think that this is an area that's very relevant to agriculture in Greece because Greece is all about fruits and vegetables. And in this space, there are lots of companies developing different types of agricultural robots. All of those robots have to be sensor-based, sensor-guided, not GPS-guided, because they have to avoid obstacles, operate under dense canopies, so there is actually no GPS signal. So precision farming is one area, and then the other area that I will talk about is labor. Now, when it comes to specialty crop challenges related to precision farming, we face sensing challenges. So the plant structure is typically very complicated, and there are problems with visibility. You can't see the fruit or the part of the plant that you want to treat. We also have a lot of biological and environmental variability in those crops, and we have a lot of complexity and variability of plant responses. So if you're building a robot that needs to, for example, take images to diagnose a certain disease and then apply the right input, it's not very easy to do so. We also face actuation challenges because plant tissue can be easily damaged, and there is also huge variability in plant physical properties. So if you want to grab a fruit or cut something or interact physically with it, this is a very difficult task. We also face limited machine accessibility because of the plant structure. Now, in terms of reduction of manual labor, I would say that the holy grail or the most wanted robots in agriculture are those that can harvest fresh market crops. Right now, every single piece of fruit or vegetable we put on our tables is harvested by hand. And the reason is that they must be picked selectively, only the ripe ones, only the marketable ones, and they need to be harvested with near zero damage because we want them to be intact, to have long shelf life. And also we want to do it very cost efficiently. We have to even beat the cost of doing it using manual labor. And these are very difficult goals to achieve. Now, we know already that in order to build cost-effective robotic harvesters, those machines need to have two main features. One is high efficiency. And efficiency means the percent of fruits or vegetables that you can harvest out of the ones that are marketable and available, for example, on the tree. Now, if you're building a robotic harvester, we have to realize that only part of the fruits will be visible. And then from those, only part will your camera vision system be able to perceive. And then out of those, your machine will be able to reach only a certain percentage. And then you will detach successfully another percentage of those and convey it back to the bin. So all of those percentages are actually multiplied in order to give you your overall efficiency. And as engineers, we know that even a weak link in this chain can kill our efficiency. For example, if you have 95% efficiency in each stage, you end up with 77% of the fruits being harvested. The rest, 23%, is all your profit. This is clearly not a good machine. Similarly, the machines need to be very fast. They need to pick many fruits per second, if you will. But if you consider that it takes time to position the robot near the tree or the bush, and then you need some time to actually perceive the crop, some time to reach it, some time to detach it, and some time to transport it. If you add up all those times, again, you can see that it's really difficult to achieve high picking speeds. So when we build harvesting robots, we need to consider both the biology and the horticulture of the problem, and also consider the design and the programming of the machine and see how we can address those as a system. Now, in many cases, it's very difficult to do that. And so an alternative is to develop machines that attack certain parts of this chain and improve the efficiency in those parts. And I will talk about some applications with robotic aid harvesters. So these are robots that are not replacing people. They are meant to work with people in order to make their work more efficient. Here's an example. Here's how we harvest strawberries in California. And I have done it myself also, but I only lasted a few minutes. It's back-breaking work. It's very difficult. Once those people finish harvesting, they actually need to walk or run back to the edge of the field in order to deliver their tray, get credit for it so they're paid, get an empty tray, and resume picking. Now, they spend 10 to 20% of their shift time just on transporting trays. So the idea behind this project was, what if we reduce this tray transportation time by using robots? And this is the actual result after a few years of work. This is, of course, fast forward. We built a couple of robots that go out to the pickers. They actually start going before a picker needs them. They show up when the picker is done. The picker puts their tray on the robot, just as you can see here, and then push a button. The robot goes away. It's all autonomous. So the picker doesn't need to walk. They just pick. Now, developing such a system was not a trivial task, both in terms of engineering, but also in terms of software and algorithms. This is a system where basically we exploited the fact that the pickers use a small cart in order to pick. We instrumented that cart so that we could measure the picked strawberries in real time, the weight of the tray. That data was relayed wirelessly to the robot fleet, and then it was also used to create a yield map. Now, when the field computer received the positions and the weights of all those carts from, say, 40 people. It used a hybrid system model of the picker activities internally and used that model in order to do model predictive stochastic scheduling so that it would dispatch the robots to meet the pickers at the right time and basically reduce the waiting time. Remember here, you may have 40 people picking, but you only have 5 robots, for example. So you really need to be very careful on how you schedule those machines. Now, we developed this system and we tested it in commercial harvesting, and we achieved efficiency gains from 12 to 20%. Work that we are doing now is targeted on the service of those robots to the pickers. I like this cartoon that I'm showing there that shows the concept of equality and equity. And so our pickers are not all the same. Some are faster, some are slower, older, younger. Right now, our robots provide service that maximizes the crew's efficiency by minimizing the make span of the overall system. But what if we could alter the software? What if we could change the objective function and offer equal or equitable service? For example, can we provide better service to the people who are slower so that they make more money during the day? So this is something we are working on now, and we already have some preliminary results that shows that properly programmed robots can actually redistribute the income so that the fast workers don't really feel any change because they're making a lot of money, but the slower, weaker workers actually see a big change in their paycheck at the end of the day. Another example of such robots is in orchards for picking fruit. This is the standard way that we do it in Greece and California with big ladders. People climb and pick trees. There are orchard platforms where you can stand on them to pick in order not to use a ladder. But the problem with these machines is that people have to stand at predefined heights and harvest from those heights, thus separating the canopy into zones. One picker harvests the upper part, another picker harvests the lower part. That can bring a problem though, because the uniformity or the distribution of fruits is not uniform. So you may end up with a fast picker assigned to a region that doesn't have much fruit and vice versa. That slows down the machine. So the idea here was to use computer vision to estimate the distribution of the fruits and then robotize this platform so that the computer, based on the demand for labor by the fruits and the supply of labor by the pickers, we monitor how fast they pick, it actually positions the pickers the right way and controls the speed of the platform in order to maximize the overall speed of the machine. And so you can see how, as the machine moves forward, the pickers are taken up and down in order for the machine to pick faster. This is a photo of the system that we built, integrated and tested in orchards. And this is a video showing the actual machine in operation, where we also achieved gain efficiencies of up to 25%. A project we are working on now relates to robotic harvesting, not robotic harvest aids. As I said, perception, reaching, grasping, and conveying are bottlenecks in the process. So we are building a multi-arm robot, and we are programming it using operational research and scheduling methods from robotics and operations research in order to maximize the throughput of all of those arms that have to be coordinated. And also in collaboration with Carnegie Mellon, we are using multiple cameras to get multiple views of the fruits in order to better estimate their spatial distribution. Now, there are lots of opportunities for R&D in robotic harvesting because we really need drastic advances in visibility and perception. Work needs to be done on multi-view imaging, active sensing, creating large data sets, hopefully novel sensing. We also need to do a lot of work on the design, the embodiment design, but also the control of multi-arm robots. Only those robots can harvest tens of fruits per second and thus be cost effective. We also need to design and control novel fruit grippers and conveyance systems, soft robots with compliance that have tactile feedback and dexterity. But like I say, the main challenge will be shown in the next slide. Most of these robotic startups will fail, especially the ones that are trying to do robotic harvesting. And the reason is that if you think about field robotics, field robots operate in uncontrolled, uncertain, unstructured environments, and it's all about them being robust and adaptable. Now, on the other hand, if you look at automation, hard automation or flexible automation, those machines operate in controlled, known, and structured environments, but we require from them high throughput and repeatability. Well, the space of agricultural robotics is actually the intersection of these spaces. We are talking about robots and automation. So these robots must be very gentle, but also be very fast, very robust, very repeatable. And all of that needs to be done in a cost-effective manner because fruits and vegetables are not high value, and also the cost of labor is still very cheap. So this is the great challenge that summarizes what we need to do in agricultural robotics in order to deploy our systems in the fields and come up with solutions to improve agriculture. And with that, I would like to thank you for the invitation again, acknowledge my funding agencies and my collaborators in the lab, and some farms that have helped us do experiments in their fields.
Stavros is going to leave now because it's 9 o'clock in the morning in California and he has to go to a class. And we'll continue now with the next speaker from an industrial world, from the Greek industry, Dr. Evangelos Theodorou, that he received his diploma in electrical and mechanical engineering from НΤУA, and then a PhD in electronic system engineering from Cambridge, 1979. He served for a while as a faculty in the School of Electrical and Computer Engineering of ΝΤУA, and then he entered the difficult industrial world, and now he's an owner and CEO of the Theodorou Group, which is one of the 80 largest industrial groups in Greece. And since 1985, he has been a leader in integrated automation solutions, which increase the productivity of the industrial packaging sector and the supply chain. Furthermore, his group offers complete robotic solutions for the end of line and the supply chain through its subsidiary, the well-known Xenon Automation Company, with more than 150 robots in operation in the largest Greek companies. The presentation will be in Greek. Κύριε Θεοδόρου, παρακαλώ.
Ευχαριστώ πολύ. Ακούγομαι εντάξει.
Μια χαρά.
Λοιπόν, ευχαριστώ πολύ για την πρόσκληση να παρουσιάσω τις εμπειρίες μας στη ρομποτική. Είμαστε μια αμιγώς ελληνική επιχείρηση. Πάνω από 40 χρόνια εμπειρία στην ελληνική αγορά, αλλά και στις εξαγωγές τεχνολογίας, η οποία χρησιμοποιείται κατά κύριο λόγο για τη βιομηχανία και την εφοδιαστική αλυσίδα. Τώρα, στη ρομποτική ειδικά έχουμε πάνω από 30 χρόνια εμπειρία και θα ήθελα να μοιραστώ μαζί σας κάποιες εμπειρίες μας που έχουμε από την εφαρμογή των ρομπότ για να λύνουμε καθημερινά προβλήματα της βιομηχανίας και της εφοδιαστικής αλυσίδας, όπως είπα. Εντάξει. Για να καταλάβουμε τι μιλάμε, εμείς, για μας, βιομηχανικό ρομπότ είναι 3 ειδών, βασικά. Έχουμε τα κλασικά ρομπότ, τα οποία μοιάζουν, οι κινήσεις που κάνουν μοιάζουν αρκετά με τις κινήσεις του ανθρώπου. Γι' αυτό και χρησιμοποιήθηκαν για να αντικαταστήσουν χειρονακτικές εργασίες στη βιομηχανία. Τώρα, ένα τέτοιο ρομπότ, αυτό το κίτρινο, συνήθως έχει 5 βαθμούς ελευθερίας. Μπορεί να φτάσει σε ωφέλιμο φορτίο μέχρι και 2 τόνους, έχουμε δει. Έχουν χρησιμοποιηθεί κατά κύριο λόγο στην αυτοκινητοβιομηχανία και τα τελευταία 20 χρόνια στη συσκευασία. Αυτό που έχει σημασία για μας είναι ότι αυτά τα ρομπότ ήταν τα πρώτα βιομηχανικά μηχανήματα που παρήχθησαν μαζικά και τα οποία είχαν εξυπνάδα. Για μας τι σημαίνει πάλι εξυπνάδα? Σημαίνει ότι μπορούν να προγραμματιστούν και μπορούν να επικοινωνήσουν με το περιβάλλον τους. Δηλαδή μπορούν να ανταλλάξουν δεδομένα είτε με άλλα μηχανήματα, είτε με χειριστές, είτε με άλλες πλατφόρμες ψηφιακές κλπ. Τώρα, όσον αφορά τα cobots δίπλα, επιπλέον θα πω ότι τα κλασικά robots ποτέ δεν δουλεύουν μόνα τους, πάντοτε τους βάζουμε διάφορα εξαρτήματα επάνω, σίγουρα πάντοτε κάποιο gripper, αλλά και άλλα έξυπνα εργαλεία και επιπρόσθετα μηχανήματα, ώστε να μπορούν να εξειδικευτούν και να κάνουν μια συγκεκριμένη δουλειά. Τώρα, στα cobots, τα cobots εμφανίστηκαν τα τελευταία 10 χρόνια. Είναι μικρά robots, πάλι σταθερά, είναι πιο αργά, σαφέστατα πιο αργά και το ωφέλιμο φορτίο είναι μικρότερο, αλλά έχουν το μεγάλο πλεονέκτημα ότι μπορούν να δουλέψουν μαζί με άνθρωπο, δίπλα σε ανθρώπους. Έχουν δηλαδή μεγάλο βαθμό ασφάλειας, σχεδόν 100%. Και τέλος έχουμε εδώ πέρα τα AGVs, τα οποία είναι ρομπότ κινητά και τα οποία έχουν χρησιμοποιηθεί κυρίως σε αποθήκες για να μεταφέρουν παλέτες, φορτία και τέτοια πράγματα, αυτόνομα μηχανήματα για βιομηχανία και τις αποθήκες. Τώρα για το ερωτηματικό που έχω βάλει εκεί πέρα θα μιλήσω αργότερα. Τώρα, έχω εδώ πέρα, ελπίζω να δουλέψει, μία εφαρμογή για να καταλάβουμε τι μιλάμε. Θα συγχωρήσετε λίγο ήχος, ίσως είναι λίγο ενοχλητικός. Λοιπόν, ελπίζω να συγχωρέσετε τον ήχο. Τώρα, αυτό που έδειξα δεν είναι ένα ρομποτικό σύστημα για μας. Είναι ένα σύστημα, ένα ολοκληρωμένο σύστημα βιομηχανικό και το οποίο το έχουμε σχεδιάσει για να κάνει μια πολύ συγκεκριμένη εφαρμογή. Το οποίο βέβαια χρησιμοποιεί 3 ρόμποτ εν προκειμένου. Άρα για μας, σαν systems integrators, τα ρομπότ δεν είναι τίποτα περισσότερο από μηχανικά εξαρτήματα, τα οποία όμως μας βοηθούν να κάνουν μια συγκεκριμένη δουλειά. Τώρα, προφανώς δεν μπορεί να έχεις μόνο τα ρομπότ εκεί, πρέπει να έχεις και πάρα πολλά άλλα μηχανήματα και εξαρτήματα και πρέπει να φροντίσουμε αυτά όλα εδώ τα μηχανήματα και τα ρομπότ να τα βάλουμε έτσι σωστά στο χώρο του εργοστασίου, ώστε να κάνουν πραγματικά τη δουλειά που θέλει ο πελάτης. Εκείνο το οποίο πρέπει, από την εμπειρία μας τώρα, θέλω να πω ότι πρέπει να ξεχωρίσουμε, σίγουρα η δουλειά μας είναι πολύ σημαντική σε αυτό, να ξεχωρίζουμε την ανάγκη που έχει ο πελάτης μας, η βιομηχανία, με τα εργαλεία με τα οποία χρησιμοποιούμε εμείς για να λύσουμε την ανάγκη, να κάνουμε το καλύτερο σύστημα που καλύπτει την ανάγκη του πελάτη. Αυτό σημαίνει ότι πρέπει να χρησιμοποιήσουμε πάρα πολλούς ειδικότητες μηχανικών. Έχω εδώ πέρα τις περισσότερες ειδικότητες μηχανικών. Θέλουμε μηχανολόγους, το πιο βασικό από όλα, από την αρχή που ξεκινάμε, είναι οι μηχανολόγοι οι οποίοι συνήθως μιλάνε με τον πελάτη και καταλαβαίνουν καλά την ανάγκη του. Οπότε φτιάχνουν τη λύση σε αρχικό στάδιο σε μπλοκ διάγραμμα, ώστε να καταλάβει ο πελάτης τη λύση που του προσπαθούμε να του δώσουμε. Μετά, εφόσον συμφωνήσουμε, πάμε σε σχεδιασμό, μηχανολογικό σχεδιασμό, ηλεκτρολογικό σχεδιασμό. Σίγουρα θέλουμε μηχανισμούς ηλεκτρονικούς που δουλεύουν σε εφαρμογές IoT, προγραμματιστές, αυτοματιστές και βέβαια και μηχανικούς παραγωγής, οι οποίοι κυρίως δουλεύουν σε εμάς σαν project manager. Απλώς να πω ότι στον όμιλό μας δουλεύουν πάνω από 90 μηχανικοί όλων των ειδικοτήτων. Τώρα, εκείνο το οποίο όμως είναι πολύ σημαντικό σε όλη τη δουλειά δικιά μας είναι να ξεχωρίσουμε σαφώς την ανάγκη που έχει ο πελάτης από τη λύση. Εμείς πρέπει να γνωρίζουμε πολύ καλά τις τεχνολογίες και να επιλέξουμε ποιες από αυτές θα χρησιμοποιήσουμε για να λύσουμε τη συγκεκριμένη ανάγκη. Άρα ο πελάτης έχει την ανάγκη του να καλυφθεί και εμείς έχουμε τις τεχνολογίες. Αν αυτά μπερδευτούν, τότε δημιουργούνται προβλήματα. Πολλές φορές έχουμε πελάτες που λέει θέλω να αγοράσω τεχνολογία. Όχι, δεν πουλάμε τεχνολογία, πουλάμε λύσεις. Είναι σημαντικό αυτό. Τώρα, για μας, ποιο είναι το μέλλον, πέρα αυτά που κάνουμε τώρα, είναι τα κλασικά. Αυτά περίπου που κάναμε και πριν από 30 χρόνια, περίπου κάνουν τα ίδια, απλώς έχουμε ίσως καλύτερα ρομπότ, πιο φτηνά, πιο γρήγορα και τέτοια πράγματα. Τώρα, το μέλλον στη δική μας τη δουλειά, τη βιομηχανική πληροφορική, όπως το βλέπουμε εμείς, είναι ότι θέλουμε να φτιάχνουμε νέα έξυπνα μηχανήματα. Δηλαδή, έχουμε τα ρομπότ που είναι έξυπνα, αλλά πρέπει να χρησιμοποιήσουμε και άλλα μηχανήματα μέσα, τα οποία παραδοσιακά δεν ήταν έξυπνα και πρέπει να τους δώσουμε εξυπνάδα, για να μπορέσουμε να τα βάλουμε να δουλέψουν όλα μαζί σαν ένα ενιαίο σύστημα. Γι' αυτό χρησιμοποιούμε να κάνουμε δηλαδή έξυπνα τα παλιά μηχανήματα ή και τα καινούργια. Χρησιμοποιούμε πολύ τις τεχνολογίες του Industry 4.0, της νέας βιομηχανικής επανάστασης. Εδώ μιλάμε πάντοτε για κάμερες, έξυπνους αισθητήρες. Έχουμε και augmented reality cloud, κοινωνιακά συστήματα κλπ. Επίσης, πολύ σημαντικό για μας είναι να μπορούμε να έχουμε στη διάθεσή μας νέες ψηφιακές πλατφόρμες και με αυτό εννοώ συστήματα ψηφιακά τα οποία μπορούν να δέχονται πάνω τους μηχανήματα με τη λογική plug and play, οπότε έχουμε δυνατότητα να βάζουμε πολλά μηχανήματα και έτσι η παραγωγική διαδικασία θα είναι μια διαδικασία Lego, δηλαδή μπορούμε να την ελέγξουμε, μπορούμε να την αυτοματοποιήσουμε, δηλαδή να βάλουμε εξυπνάδα, ώστε πολλές φορές αυτό το σύστημα που παραδίδουμε να είναι αρκετά ευέλικτο και να μπορεί πολλές φορές και να αλλάξει, γιατί οι ανάγκες βιομηχανίας δεν είναι σταθερές. Οι περισσότερες βιομηχανίες μετά από 4-5 χρόνια ερχόνται σε εμάς και ζητάνε κάποιες αλλαγές, ή μικρές ή μεγαλύτερες. Τώρα, οι ευκαιρίες που έχουμε τώρα εμείς, αυτό που σαν ελληνική επιχείρηση, για μας η βασική ευκαιρία είναι ότι μπορούμε να αναπτύξουμε περαιτέρω τεχνογνωσία σε υπάρχουσες εφαρμογές, κλασικές αλλά και στις νέες που είπα, και σε αυτό μπορούμε να το κάνουμε πολύ καλά στην Ελλάδα. Δεν χρειάζεται να φτιάξουμε ρομπότ στην Ελλάδα, τα έχουμε έτοιμα. Αυτό όμως που χρειάζεται είναι να έχουμε μηχανικούς εξειδικευμένους που να τους εκπαιδεύσουμε κι εμείς, αλλά να θέλουν να μπουν και στο χώρο, ώστε να μπορούν να εφαρμόζουν σωστά τη ρομποτική για βιομηχανικές εφαρμογές. Και αυτό το οποίο για μας, αυτό που αναγνωρίζουμε τα τελευταία χρόνια, είναι ότι η μεγάλη αλλαγή είναι ότι πια η βιομηχανία γίνεται digital. Οι ψηφιακές πλατφόρμες που είπα προηγουμένως και όλα αυτά, είναι πολύ σημαντικό να καταλάβουμε ότι η πραγματική αλλαγή που έρχεται και η οποία ήδη έχει εφαρμοστεί σε μερικές περιπτώσεις είναι το ψηφιακό εργοστάσιο. Πάρα πολύ σημαντικό για μας. Επίσης, στην επιχείρησή μας έχουμε αποδείξει ότι μπορούμε να κάνουμε εξαγωγές. Έχουμε βάλει ρομποτικά συστήματα από την Αγγλία, τη Σκωτία μέχρι τη Σαουδική Αραβία και με πολύ μεγάλη επιτυχία. Επιτυχία για μας σημαίνει ότι ο πελάτης ξανάρχεται να βάλει και δεύτερο και τρίτο σύστημα. Αυτό σημαίνει ότι είναι ευχαριστημένος. Τα προβλήματα που έχουμε, κατά κύριο λόγο, είναι ότι εάν ακούσει κανένας ότι εδώ αυτό το σύστημα είναι ελληνικό, στην αρχή έχει επιφυλακτικότητα μεγάλη. Αυτό σημαίνει ότι πρέπει να δουλέψουμε παραπάνω στην λύση που θα δώσουμε, ώστε να υπερβούμε πολλές φορές τις απαιτήσεις των πελατών, τις προσδοκίες τους. Και αυτό το επιτυχάνουμε, αλλά αυτό το θεωρούμε και πολύ αρνητικό, γιατί βοηθάμε και τους εαυτούς μας να γίνουμε καλύτεροι. Και βέβαια το μεγάλο μας πρόβλημα είναι ότι δεν έχουμε εξειδικευμένους μηχανικούς. Δηλαδή είναι πολύ λίγοι, βάζεις μια αγγελία να βρεις μηχανικούς και δεν έρχονται πολύ. Ή και αυτοί που έρχονται δεν είναι ακριβώς να καταλάβουν το αντικείμενο, να θέλουν να μπουν στο αντικείμενο. Γι' αυτό και θα θέλαμε πολύ τα πανεπιστήμια να βγάλουν περισσότερους εξειδικευμένους μηχανικούς. Τώρα, εντάξει, έχω βάλει και μερικά πράγματα εδώ για την επιχείρησή μας. Έχουμε 200 εργαζόμενους και έχουμε εξαγωγές σε περίπου 15 χώρες και πιστεύω ότι θα προχωρήσουμε παραπέρα. Και έχουμε περίπου 20.000 εγκαταστάσεις, καλύπτουμε και όλη την Ελλάδα, την Κύπρο, αλλά και παρότι έχουμε συμβόλαια με πελάτες που έχουμε εγκαταστήσει μηχανήματα στο εξωτερικό, μπορούμε να τους καλύπτουμε μια χαρά και από την Ελλάδα ή και από τοπικούς αντιπροσώπους. Ευχαριστώ πολύ. Ελπίζω δεν έχασα πολύ το χρόνο.
Μια χαρά. Ευχαριστούμε πολύ, κύριε Θεοδόρου. And now we proceed to our last speaker, Professor Michael Triantafyllou. He's the last, but of course not the least, because he's the William Koch Professor of Marine Technology at the Massachusetts Institute of Technology and the director of the Center for Ocean Engineering in the Department of Mechanical Engineering. He's a graduate of НΤУA from the Naval Architecture and Marine Engineering Department, and he obtained a doctorate of science in ocean engineering from MIT in 1979. His research is in the areas of biomimetics, dynamics, and control of marine systems, and experimental fluid mechanics. He pioneered the biomimetic robots to study the basic mechanisms of flow control that lead to the outstanding agility of fish and cetaceans. As a result of this in his robot, as a result of this effort, it was his robot tuna design, a very well concept in the field of marine robotics. He's currently studying the physics of low sensing and efficient marine mammals to achieve supermaneuverability. He has also an impressive consulting record to worldwide technology leading businesses. Mike.
Thanks for the introduction, Costa, and it's a pleasure to be with you. What I will try to do is to outline some of the developments in robotics and AI in ocean engineering, which have led to a lot of startups. And I will grab this opportunity to provide the impetus for young Greek scientists to turn into the startup mentality and culture. Just to give you an idea of how this culture has changed at MIT, a report came in 2015, which pointed out that only 4% of MIT graduates in the 1960s opened a new company, a percentage which went to 8% in the 1990s. And then by 2015, it was 25%. So it's clearly a tremendous change of focus for the graduates of engineering at MIT and everywhere. MIT is one of many centers for such development. The result you can see, there were about 104,000 living graduates in 2015 from MIT. They had founded 30,000 active companies, which were employing 4.6 million people, producing about 1.9 trillion in income annually, which was just below the annual GDP of France. So there is tremendous potential, and I would like to take my limited opportunity in the area of ocean engineering, which for Greece is not limited at all because Greece is surrounded by the sea, and there are many opportunities there. So this will be the primary focus today. There is a joint program between the Woods Hole Oceanographic, which is an oceanographic institution not too far from here, and MIT, which prepares candidates for working in the ocean in various capacities. As a result of this program, over the last 25 years, a whole belt of startups and which developed into larger companies exists around Woods Hole primarily and in Boston as well. So there are recognizable names such as Benthos, Bluefin Robotics, which came out of MIT, and many others with substantial business which started on a small scale. So I've seen all of these developments, and I would like to point out where the opportunities may be in the future. This is an outline of the early developments of autonomous underwater vehicles. The Remus is a very well-known autonomous vehicle developed at Woods Hole, and Odyssey was developed at the Sea Grant program at MIT, which I direct right now. And these two almost monopolize certain aspects of the market. The gliders were developed even earlier. These are devices which can be developed with a relatively small budget. It's the idea that counts. And these gliders achieve phenomenal performances, such as sending one of those gliders from Boston to Bermuda and utilizing the very ingenious concept of gliding and control through buoyancy control to observe the ocean over very long times and distances. Likewise, this autonomous vehicle, surface vehicle with solar panels can be out in the ocean for months, observing continuously the ocean. All of this, when we were developed, were at a very low budget, but ingenious solutions level, the kind of thing that can be used as an inspiration. Applications many. I have here some ocean archaeology. I was involved in this one, which explored a wrecked ship outside Nisyros. This is the wreck of the Elefanto. The offshore industry is employing many vehicles. It has a continuous demand for observation and manipulation, inspection of ships. So the market is really significant, despite the fact that it's addressed to a very specific environment. So what is next? What is coming next? Autonomy. Autonomy is what enables observation of the ocean. We know less about the ocean than we know about the moon. Observing the ocean of the South Pacific hasn't been done since Captain Cook were there with his ship. So we need to develop coordinated observation of the ocean. This is one particular application where they used 12 Remus AUVs coordinated with 2 Nekton, 2 surf crawlers, and so on, and several buoys to perform a specific mapping for ocean acidification. Another new market, autonomous surface vehicles, again for observation. Here are some concepts that I'll show you. They started at Sea Grant, which I direct, as I told you, back in 1993. They were very simple models, and they developed as we go along. You see this Scout was at also in the Department of Mechanical Engineering, and leading to more and more industry-ready designs. To arrive today, where we had recently acquisitions such as the liquid robotics for $300 million. This is a very ingenious concept where there is a surface vehicle and an under submerged structure. And when the surface vehicle moves in waves and the surface at the bottom does not, produces energy. It's equipped with solar panels, so we can have observation of the ocean over very long scales. And there are several of such products right out of Sea Grant that I have observed as they have been created and then generated into larger companies. So today we are dedicated to autonomy as a concept, and again, concepts such as an autonomous sailing boat, which will be using sails to go for very long distances. A very simple concept, extremely effective, with solar panels to provide the control function, or autonomous surface vehicles to go and collect data, which we need in the ocean without having to employ humans. So this is an area of tremendous growth, and it will be so for the next 10 years at least. For example, on the left, you see the map with the buoys that are observing the ocean. And these buoys were designed and installed by NOAA, the National Oceanic and Atmospheric Administration, at great expense. If one of these buoys needs to be repaired, it needs something of the order of $300,000 to repair it. And look on the right-hand side, a company called SOFAR has developed a simple buoy, $5,000, which now there are 1,000 of them, and look how much more of the ocean is covered by this simple buoys compared to the expensive NOAA ones. One small revolutionary idea, which will allow us now to observe unobservable parts of the ocean previously. The industry for observing the weather is already $7 billion because there is a great need to know what the weather will be with accuracy. So I'm sure this will become a reality in every ocean, including the Mediterranean. Another area of potential growth for Greece is the decarbonization of ships. Ships have to reduce emissions by 40% in 2030 and 70% by 50. And this means we have to come up with completely novel designs. Well, Norway and Australia are already preparing autonomous ships which are electric, all electric. So they have no carbon footprint, but autonomy is essential. And you have to remember, autonomy doesn't mean unmanned. You can have a very much reduced crew. So imagine all the ferries that are in Greece with distances which do not exceed 150, 200 miles, which is the range of such ships, being replaced by such new concepts. Why leave it to Australia, which is always at the forefront of new concepts? Many of the modern ferries are designed in Australia, and the Norwegians who are extremely capable at coming up with such devices. And by the way, there are many concepts to be installed on ships. Michelin, the French company, recently came up with specially designed sails. The Flettner rotors, which if you have had fluid mechanics recently, you may remember them as a curiosity from fluid mechanics books. They've been installed in ships. The ship here on the right is a Greek ship. So here is where we need ideas to which all they need is special attention to address a specific need. Another area which is of tremendous growth is devices to enjoy the ocean. I'll show you a very short clip from a brand new device. I have been involved with the design of some of these devices.
This is an electric hydrofoil surfboard, which can fly above any body of water at speeds of up to 25 miles per hour. The electric hydrofoil surf.
This is a great opportunity. We have oceans which are really conducive to the use of such devices, of such devices. These have come up in the last 5 years, and there's tremendous growth. This they cost something like $7,000 or $8,000, and you can go 25 miles per hour, unheard of before, with a simple control, handheld control. And the design is more akin to aircraft than to marine vehicles. So I would like to point out this as an area where you can have fun and you can have really ingenious idea. I'm involved with some of these people, and I know it takes dedication, but the results are really tremendous. Another topic is that the ocean can feed the world. The ocean has the same biomass as land, but only 2% of the food comes from the ocean. So the opportunity is to expand this, but we cannot do it by wild catch. That has saturated. We don't want to kill the fish. So we have to turn from hunters and gatherers of the ocean to ocean farmers. And this is in the works. Here on the right, you can see the new platforms that has been designed in Norway. On the left is a robot that flips the bags. Something that is happening today by hand. This is a farm in Massachusetts. So we listened to the farmers, to the aquaculture farmers. They told us this is the great need. So I had my class last year, where I teach electromechanical system design, come up with this robot. And we went down to the farm and demonstrated it can be done. So right now we're talking with companies who are going to commercialize this concept. So it's, we have developed all the computer vision and the like to identify the bags and the like. So it has all the paraphernalia needed to be able to do this. But all you need to do is to tune to the customer, to the need. And then the ideas spark up. There is a special company called CIAHEAD, which has a program called Blue Swell, which is just to provide funding for startups in the ocean. On March 2nd, there is the big meeting where they will announce the winners of this time. We need more of these efforts in Greece as well. It's a cultural change. And talking about cultural change, we need maker spaces. Here you can see the map of MIT, and these are red spaces are all maker spaces where every student can go, any member of the faculty and the staff can go and try new concepts. So I hope this will inspire you to become entrepreneurs and open startups. Thank you.
Okay, thanks a lot, Michael. And now we are moving to the last session of today's presentation, which is going to be led by Professor George Pappas of the University of Pennsylvania, where he is the chair of the Department of Electrical and Systems Engineering, with interests in control theory and a lot of awards. George.
Thank you, Kostas. On behalf of all the organizers, I would like to thank the speakers. They were fantastic presentations. I actually learned a lot today. Given that we are a little bit late, I think we're going to skip a little bit the summary statements. But what I do want to summarize a little bit a message that I saw across all the presentations is that robotics is in a great state. It's a great time to focus on robotics. There is amazing new developments happening on the interactions with AI or IoT or bridging the analog and the digital divide, as was mentioned. I think it is a technology that can impact many societal areas, whether that is agriculture or maritime, as we just saw, or security, as well as logistics and industrial robotics, as we saw from Dr. Theodorou. And I think a lot of these areas can have societal impact in Greece as well as the rest of the world. And I think what our goal here is to really, create a community of researchers that can think about across science, research, but also innovation, how to create that ecosystem across the Atlantic, across academia and industry divides. And I hope we have a chance of continue this interaction. There's a great opportunity for innovation, as was just mentioned by Professor Triantafyllou, as well as Professor Stefanakis earlier. I think it's a great opportunity to continue this discussion. And on that behalf, on that role, I would like to also welcome all of you to the first HIAS conference that will happen on July 8th. At the Eugenides Foundation in Athens, Greece. I'm sure there will be also some remote participation as well. But for more details about how to engage, participate, please follow the HIAS website, where we'll be coming up with a program, an exciting program, as well as ways by which we can continue this discussion. I think on that behalf, I would like to thank everyone again, as well as the audience for some fantastic questions as well. And looking forward to seeing you, not virtually, but also in person in the future. Thank you very much.
One last thing before we conclude that session is that I would like to thank Mr. Ziggounakis from ΝΤUA, who handled the technical aspects of this, and Associate Professor Babis Behliouli from University of Patras, who handled the questions. Thank you very much, and we'll see you somewhere in the robotics world. Have a good night.
Thank you.
Good night. Thank you.
Good night.
Thank you. Bye-bye.
Bye.
Bye.
Goodbye.